Alright folks, next mini lecture. This is 1-5 to 1-6. So 1-5 and 1-6, and it's basically about homeostasis. Now, homeostasis, this is the key principle of physiology. Extremely important. Matter of fact, this picture I'm about to explain to you, you're going to see over and over and over again throughout the different organ systems. Now, you won't see thermostat and air conditioner, but you'll see the concept. So let me just tell you first of all, the definition of homeostasis is maintaining a relatively constant internal environment. So internally, you're staying in equilibrium. But what it is not, it is not equilibrium with your environment. And I've read texts that incorrectly say that. I mean, just think about it. Do you really think that your blood has the same amount of glucose as the air around you? It just doesn't. Your temperature isn't the same temperature as the air around you. I mean, on some days it might be, but most days, like in January, the air around you is very, very cold, and your body's still 37 degrees Celsius. And even in the summertime, usually the temperature isn't 37 degrees Celsius, 98.6 Fahrenheit. It's been up close to that. It's been in the 90s this summer, but it usually is not that high. So homeostasis is a relatively constant internal environment. It is not equilibrium with the environment. Matter of fact, it's disequilibrium with the environment. But it's maintaining a constant internal condition. Here's how it works. We have a homeostatic we have homeostasis. That means whatever variable we're looking at, it is in normal range. Well, let's talk about normal range. You see this, we're talking about temperature here in the y-axis. It could be any variable. It could be potassium, it could be calcium, it could be glucose, it could be pH, it could be osmolality, it could be any variable in your body. And what we have is a set point. But because of our homeostatic mechanisms, we can deviate a little bit below the set point and a little bit above the set point, and a little bit below the set point, and a little bit above the set point. And it's because our homeostatic mechanisms take a little bit of time to kick in and adjust, and kick in and adjust. Because of that, we have what we call a normal range. It's the normal physiological range that's above and below the set point. So homeostasis is defined as that variable being within the normal range. And on purpose, not by accident. I mean, that variable is within normal range because your mechanisms are working to keep it that way. So it's not the old adage, even a broken clock is right twice in a day. It's not that old broken adage. The homeostasis is you are correct on purpose, not by accident. So we're at homeostasis. We're within the normal range on purpose. Something disturbs that variable. In this case, we're talking about room temperature going up. Well, there has to be a receptor that detects that the temperature is getting hotter. So we have a receptor. In the case of your house, you have a thermometer. Now, the thermometer is usually within the thermostat, by the way. See, this is the thermostat, the control center. That's what's going to make your furnace kick on or make your air conditioner kick on. However, in your house, your thermostat, your thermometer is probably inside the thermostat. You probably have a thermometer right in here, all right, just so you know. And actually, let me erase what I just drew there, because likely what it is, at least this is what how I've seen mine, is you have a horizontal tube filled with mercury or graphite, and the temperature of this tube can tilt this up or down, and it kicks on the circuits or kicks them off, one or the other. So you have a thermometer, which is a receptor. That receptor detects the deviation from normal. Now you have a control center. That's your nervous system in the body. In your house, the control center is the thermostat. It's the one that's going to either kick on your furnace or kick on your air conditioner. The control center is, the receptor talks to the control center and says, hey, I'm too hot or I'm too cold. The control center sends a command signal to an effector, something that has the ability to raise or lower the temperature, like your furnace or your air conditioner. So the control center itself doesn't blow out cold air or blow out hot air, But the control center tells the effector, blow out hot air, blow out cold air. And the effector then does what it's told. So if the temperature in your house goes up, your thermometer, the receptor detects it, that tells the control center I'm too hot. Control center turns on the air conditioner, which is your effector, and your air conditioner drops the temperature back to normal. This is a homeostatic mechanism. Now, in homeostasis, we usually break it down and talk about intrinsic or autoregulation versus extrinsic or central regulation. Now, central means the nervous system. So what do I mean by intrinsic or autoregulation? Well, it could be something as simple as this. If my stomach stretches, I have a signal, a local signal that makes my stomach contract. I didn't have to involve my brain or the nervous system well, I better be careful when I say nervous system there. I didn't have to involve my central nervous system. So that's an intrinsic or autoregulatory mechanism. It's still a homeostatic mechanism. It's a local mechanism that doesn't have to involve the central nervous system. And in addition to local or autoregulation, we have extrinsic regulation, which does involve the brain and spinal cord. So I'm showing you a digestive video. You're not going to cover the digestive system until you take Bio 252. So please ignore the digestion terminology, if you will, and just look at the concept of autoregulation and extrinsic regulation.
Regulation of stomach secretion is divided into 3 phases: cephalic, gastric, and intestinal. In the cephalic phase, the taste or smell of food, tactile sensation of food in the mouth, or thought of food sends nervous impulses to the medulla oblongata. These impulses cause parasympathetic neurons via the vagus nerves to stimulate secretion of hydrochloric acid and pepsinogen in the stomach. The parasympathetic stimulation also results in secretion of gastrin from the lower part of the stomach. This hormone travels through the bloodstream and further stimulates hydrochloric acid and pepsinogen secretion in the upper and middle parts of the stomach. In the gastric phase of gastric secretion, food has entered and distended the stomach. This distension activates a parasympathetic reflex via the medulla oblongata and also has a direct stimulatory effect on the gastric glands.
Okay, right there. This stretching has local reflexes. You don't have to go through the brain or spinal cord. This is an autoregulatory mechanism, whereas the vagus nerves loop here is an extrinsic regulation. Now what you're going to say to me is, well, they're both occurring. Exactly, they're both occurring. And in many of these systems we're going to study, there's intrinsic regulation, also known as autoregulation, and there's extrinsic regulation, which involves the central nervous system. Now I just wanted to show you that. I'm going to finish the video just in case you want the video finished.
The result is continued secretion of hydrochloric acid and pepsinogen. In the intestinal phase of gastric secretion, chyme has entered the duodenum, so gastric secretion is no longer needed. When the chyme contains lipids from the digestion of fats or contains enough hydrochloric acid to bring its pH below 2, gastric secretion is inhibited. The lipids and hydrogen ions inhibit gastric secretion by 3 simultaneous actions. First, they cause impulses to go to the medulla oblongata to decrease parasympathetic stimulation of the gastric glands. Secondly, they set up local reflexes via neurons in the wall of the gut that decrease gastric secretion. Thirdly, they cause the release of 3 local hormones which travel via the circulation to the gastric glands and inhibit their secretion.
All right, folks. Now you will do digestive system and Bio 252. This video will be nothing for you by the time you study the digestive chapter. But for our purposes, I just wanted to show you the difference between autoregulation which is local, also known as intrinsic, and extrinsic regulation, which involves the central nervous system. Oh, by the way, or it could be the endocrine system as well. So when I said extrinsic regulation is the central nervous system, I suppose it could also be the endocrine system. However, I would still argue that that still has to involve the central nervous system. And why would I say that? Because the hypothalamus tells the pituitary what to do, and the hypothalamus is part of the brain. So I would still argue that it involves the central nervous system. All right, so how do we maintain homeostasis anyway? Well, the main way we maintain homeostasis is by what we call negative feedback. Now, is there such thing as positive feedback? You bet. There's a half a dozen to a dozen positive feedback mechanisms in your body, but there's hundreds of negative feedback mechanisms in your body. Hundreds, maybe even thousands. I've never really tried to count them, but there's lots of them. In fact, if you looked at the negative feedbacks in biochemical pathways, metabolic pathways, then certainly there is thousands of negative feedback pathways, because all your metabolic pathways have negative feedback mechanisms. So let's look at that. Well, what negative feedback is, let's do that first, is you're at homeostasis, but there's a stimulus that makes you go outside of homeostasis. Negative feedback must reverse that stimulus. It must. If your response doesn't reverse that stimulus, that's not negative feedback. And in fact, let me just tell you what positive feedback is. Positive feedback is enhancing or exacerbating the original stimulus. All right. So, what's my original stimulus? Body temperature is rising. Well, I better have a receptor that detects that, and I do. I have temperature sensors in my skin, and I have a hypothalamus, which is part of my brain. And I have thermometers in my brain that check the blood flowing by it to see how warm it is. So I have receptors in my skin and in my brain. Now, if my blood or cerebrospinal fluid or other fluids, interstitial fluid, if these fluids are too warm, they send a signal to the thermoregulatory area of my brain. The thermoregulatory area of my brain happens to be my hypothalamus. That's this word right here. Now what you're going to say to me is, I thought the hypothalamus was a receptor. I'm going to say to you, the hypothalamus is like a thermostat. It contains the thermometer and it's the control center. Now, does it contain the thermometer for everything? No, it doesn't. It contains the thermometer for temperature and for saltiness, what we call osmolarity or osmolality. But it doesn't contain the thermometer for blood glucose. You know, the blood glucose level is controlled another way. So my hypothalamus can be a receptor, and it certainly is a control center. Now what happens? My brain, or hypothalamus in this case, sends signals down that reverse the rising body temperature. Well, how do you reverse your rising body temperature? You know, sweat. You know you sweat when you get warm. Something you probably don't know is, and you might have seen this in the gym, why does someone's face get real red when they start working out? And the reason for that is you dilate blood vessels in your skin. Why would you dilate blood vessels in your skin? More blood flows to your skin, and then the heat leaves your body because you're sending more really warm blood to the surface of your body. So my effectors are sweating and dilating blood vessels in my skin to get rid of heat. What does that do? That brings me back to normal. Alright, so that's negative feedback. The typical way I maintain homeostasis is by negative feedback.
During the menstrual cycle, before ovulation, small amounts of estrogen.
I'm going to back that up and start it again. Let me just pause and say this. Like the digestive video, this is a reproductive video. You don't need to know all the nomenclature that you're going to hear. You're going to hear a bunch of nomenclature. You're going to hear a bunch of hormones like follicle stimulating hormone and luteinizing hormone, etc. Please don't worry about that right yet. Just look at the positive and negative feedback loops that you'll see. All right, and I'll actually stop the video and point out a positive feedback loop, and I'll stop the video and point out a negative feedback loop.
During the menstrual cycle, before ovulation, small amounts of estrogen are secreted from the ovary. Estrogen stimulates the release of gonadotropin-releasing hormone from the hypothalamus and luteinizing hormone from the anterior pituitary. Gonadotropin-releasing hormone also stimulates release of luteinizing hormone from the anterior pituitary. Luteinizing hormone, in turn, causes release of additional estrogen from the ovary.
That's positive feedback. Let me just repeat what he just told you. He said that you're secreting estrogen from the ovary. And the estrogen goes up and turns on GnRH, gonadotropin-releasing hormone from the hypothalamus. Estrogen also goes up to the anterior pituitary and increases LH, luteinizing hormone. By the way, meanwhile, GnRH goes to the anterior pituitary and says, make and secrete luteinizing hormone. So in essence, estrogen is turning on a whole bunch of luteinizing hormone, either directly or indirectly through GnRH, gonadotropin-releasing hormone. Okay. What does luteinizing hormone do? It causes the ovary to make more estrogen. That's a positive feedback loop. You didn't reverse the original stimulus. You enhanced or exacerbated the original stimulus. That's a positive feedback loop. Now, as it turns out with this system, when the estrogen gets to a certain level, a threshold level, it quits having a positive feedback effect and it starts having a negative feedback effect, and it shuts down GnRH and it shuts down LH. Now I'll let him tell you.
The levels of gonadotropin-releasing hormone and luteinizing hormone increase in the blood due to this positive feedback effect. After ovulation, the corpus luteum is formed in the ovary and begins to secrete progesterone in response to luteinizing hormone. Progesterone inhibits the release of gonadotropin-releasing hormone from the hypothalamus and luteinizing hormone from the anterior pituitary. Blood levels of gonadotropin-releasing hormone and luteinizing hormone decrease because of this negative feedback effect.
All right, there you go, folks. That's a negative feedback and a positive feedback in one video. You will be an expert at this video when you get to chapter 28 in Bio 252. Okay, so positive feedback. It exists. It's not as common as negative feedback, but it does exist. Remember, positive feedback must enhance or exacerbate the original stimulus. So what's one example of positive feedback? And the answer is blood clotting. All right, what happens? I break my blood vessel. Here's my endothelium right here, and it's broken, so I'm bleeding. All right, underneath my endothelium, I have some collagen and some smooth muscles around my blood vessels. These cells, these fibroblasts and these smooth muscle myocytes, and even the endothelial cells, they'll secrete some chemicals. These chemicals are chemoattractants for platelets. These are platelets right here. So these chemicals call platelets to the area. Now, the platelets themselves secrete more chemicals, which call more platelets. So you can see that the more platelets that aggregate, the more platelets that are called. Now, when does it stop? It will stop when this collagen is covered up. So when you cover up the collagen like you see here, now these platelets here will quit releasing the chemicals. And you won't call any more platelets to the area. And now you start this whole clotting process. Because a platelet plug is not a clot. A platelet plug is a beginning of a clot. And then you have to do this clotting process called the clotting cascade, which you'll learn in chapter 19. We're not going to do the clotting cascade right here. So blood clotting is a positive feedback loop.
Increased blood pressure stretches the carotid arteries and aorta, causing the baroreceptors to increase their basal rate of action potential generation.
Baroreceptor means pressure receptor. Baro means pressure. So baroreceptor is a pressure receptor. Now, you will do this chapter this semester, but again, don't worry about all the nomenclature of the glossopharyngeal nerve and the vagus nerve and all of that. Don't worry about it. Just look at the negative feedback. If my baroreceptors are saying my blood pressure is too high, there will be a negative feedback that lowers my blood pressure. If the baroreceptors say my blood pressure is too low, there will be a negative feedback that raises my blood pressure. So let's just look at that.
Action potentials are conducted by the glossopharyngeal and vagus nerves to the cardioregulatory and vasomotor centers in the medulla oblongata. As a result of increased stimulation from the baroreceptors, the cardioregulatory center increases parasympathetic stimulation to the heart, which decreases the heart rate. Also, as a result of the increased stimulation from the baroreceptors, the cardiovascular center decreases sympathetic stimulation to the heart, which decreases heart rate and stroke volume. The vasomotor center decreases sympathetic stimulation to blood vessels, causing vasodilation. The vasodilation, along with the decreased heart rate and decreased stroke volume, bring the elevated blood pressure back toward normal. If the initial problem were a decrease in blood pressure, the activities and effects of the baroreceptors, cardiovascular center, and vasomotor center would be the opposite of what is illustrated.
All right, I want to go back to this part right here. So I hate how he just, at the very end, just says, oh, by the way, if the blood pressure went down, it would be the opposite. So let me talk you through it. If blood pressure is too high, I have receptors right here. They're called baroreceptors, and they're in the aortic arch and in the carotid sinus right there. All right. They send the signals to the central nervous system right here in the brain stem, the medulla oblongata, in other words. They're saying to the brain stem, they're saying, hey, blood pressure's too high. So this is the control center. Now what does the control center do? It sends out signals that lower blood pressure. One signal it sends out, it says, don't go fast. See, I shut down this signal, and I say, don't beat fast. I turn on this signal, and I say, beat slower. And I turn on this signal, and I say, vasodilate, which is like taking a water hose and making it big. And you know what happens if you have a hose, a garden hose in your garden, and you have water coming out of it. If you narrow the end of the water hose, the water comes out more forcefully, higher pressure. And what you can't really do is, if you made the hose big, the water would just trickle out and you'd have lower blood pressure, lower pressure. So the same thing happens in your blood vessels. If I dilate my blood vessels, I get lower pressure. Now, if the pressure was too low right here, then my baroreceptors send a signal to my brain stem, my medulla oblongata, my central nervous system, and it says my blood pressure is too low. In this case, I would send a signal up this red nerve right here, and I'd say beat faster. I would send signals down through here, and I'd say constrict, vasoconstrict. So you can see I could do that. I could raise my blood pressure. All right, that's homeostasis. Now, the organ systems in your body all have some form of homeostatic regulation. Every one of them is going to have some form of homeostatic regulation. Probably the hardest one to look at something with homeostatic regulation is the reproductive system, because it's not really there to maintain homeostasis. It's there to have babies, and in essence it takes you out of homeostasis quite a bit. For example, the reproductive system puts you in puberty. The reproductive system pushes the baby out of the uterus, and that's positive feedback. But I could even think of some examples of homeostatic regulation from the reproductive. But look at these. Look at all these systems. They all have some homeostatic mechanism. Sure they do. All the systems have homeostatic mechanism. By the way, is the reproductive in here? No, it's not. That would be the hardest one. Reproductive for me would be the hardest one to come up with a homeostatic mechanism. But you know what? I'll think about it and give you one in lab, because I know it has one. That's it. The rest of chapter 1 will be forthcoming.